In August of 1883, the world heard a sound so violent it traveled around the planet. Krakatoa did not simply erupt, it tore itself apart. The explosion shattered an island, sent tsunamis racing across the sea, darkened skies thousands of miles away, and left behind one of the most terrifying volcanic scars in human history. For generations, Krakatoa became a warning, a name whispered whenever the earth reminded us that the ground beneath our feet is not dead. But the most frightening part of Krakatoa's story is not what happened in 1883. It is what came after, because from the ruins of that destroyed island, a new volcano began to rise from the sea. Year after year, eruption after eruption, it grew, and now the volcano born from Earth's most violent eruption is stirring again. Smoke is rising, the crater is restless, the island is changing, and scientists are watching closely because Krakatoa is not just another volcano waking up, it is a volcano with a memory of catastrophe. So, what is really happening beneath Krakatoa? Why is it waking again? And could the same volcanic system that once shook the entire planet be preparing to remind the world what it is capable of? This is the story of Krakatoa, the volcano that destroyed itself, returned from the sea, and may not be finished yet. If you enjoy content like this, hit the like button and subscribe. And if you feel like sharing, let me know in the comments. What town, city, or country are you watching from today? And what's the time there? I enjoy seeing how far across the globe these stories travel. Settle down and let's begin. Some stories become so familiar that they seem complete, polished by repetition, until every major moment feels settled. Krakatoa often exists in that form, remembered through a handful of extraordinary facts that have echoed across generations. The tremendous blast traveled farther through the atmosphere than any sound reliably documented in recorded history. More than 36,000 people lost their lives. A pressure wave circled the planet several times. Brilliant sunsets colored distant skies across Europe for many months, turning ordinary evenings into reminders that an eruption on the opposite side of Earth could still leave its mark. Those details deserve their place in history, yet they are only the opening movement of a much longer geological story. During the morning of 1883, the volcanic island standing in the Sunda Strait between the islands of Java and Sumatra reached the end of an immense buildup of pressure. Explosive eruptions shattered much of the island within hours, driving enormous volumes of ash, volcanic gas, and fragmented rock into the atmosphere. The surrounding sea responded with destructive tsunami waves that swept across nearby coastlines, removing more than 165 villages and reshaping countless lives in a single day. Few natural events have altered both landscape and memory with such lasting force. When the eruption finally exhausted itself, the geography of the region had changed beyond recognition. The volcano that had dominated the strait no longer stood where generations had known it. In its place remained a broad depression carved into the seafloor, a caldera reaching about 270 meters, which is about 886 feet below the ocean surface, and stretching roughly 7 kilometers, which is about 4.3 miles, across. The collapse revealed that an eruption of sufficient size can erase the mountain that produced it, leaving only the outline of its former presence beneath the water. Along the edges of that immense hollow, three fragments endured. Rakata, Sertong, and Panjang remained above the sea as weathered reminders of the larger volcanic complex that had once occupied the strait. Their cliffs and ridges marked the surviving margins of a structure whose center had disappeared, preserving only pieces of a landscape that earlier maps could no longer fully describe. Looking across the water afterward, It would have been understandable to imagine that the volcanic chapter had reached its conclusion. The surface offered little evidence of continuing activity. Ships resumed their routes, charts recorded the altered coastline. Daily life slowly found a rhythm again around a place forever changed. Far below those waters, however, the deeper engine of the region continued its patient work. Molten rock was still being generated through the ongoing movement of tectonic plates, gathering within pathways that had not vanished with the island above. The caldera resting beneath the waves marked an ending visible from the surface, yet it also formed the setting for another beginning that remained out of sight. That continuing story is where this journey now turns. The famous eruption belongs to history, but the volcanic system that produced it never truly reached its final page. Everything that follows grows from the landscape left behind after the destruction, where an empty space beneath the sea gradually became the birthplace of an entirely new volcano. The passing of years can reshape memory as thoroughly as lava reshapes stone. Across the Sunda Strait, the devastation left by the eruption gradually gave way to ordinary routines. Harbors welcomed vessels once more, rebuilt settlements settled into familiar rhythms, and children inherited stories of a volcano they had never seen with their own eyes. For those born after the catastrophe, Krakatoa belonged increasingly to family recollections instead of daily experience, its absence becoming almost as familiar as its former presence. From the closing months of 1883 until the final weeks of 1927, the caldera remained without any significant eruptive activity. Its broad depression rested beneath the sea, while the surrounding region continued rebuilding. Dutch colonial authorities restored damaged coastal communities where rebuilding proved possible, and trade resumed through one of Southeast Asia's most important maritime passages. Mariners relied on newly prepared navigation charts because the eruption had permanently altered the shape and depth of the seafloor. Every voyage acknowledged a landscape transformed, even if the ocean surface revealed little of what lay below. Nature also began writing its own record across the surviving islands. Rakata, Sertung, and Panjang, stripped almost completely during the catastrophe, gradually welcomed life again. Spores drifted on the wind, seeds floated across the water, insects arrived through chance journeys, followed by birds and other animals that carried new generations of plants with them. Scientists documented this remarkable return with unusual care, creating one of the most complete observations ever assembled of ecological succession. Bare volcanic rock slowly developed into living communities, offering researchers an opportunity that rarely appears so clearly within a human lifetime. As decades passed, the people who had witnessed the eruption entered old age. Their children listened to first-hand accounts, while another generation encountered the event through local tradition and written history. The volcano remained an important landmark within memory, although each passing year placed another layer of time between the living world and the destruction that had reshaped it. Geologists and volcanologists continued observing the caldera whenever possible. Their instruments and field surveys recorded occasional earthquakes, each reflecting the natural restlessness of an active tectonic region. None of those small movements suggested that another volcanic structure was preparing to emerge. The observations remained consistent with a system resting between major episodes, offering no obvious indication that change had already begun at greater depth. Far below the seafloor, the broader engine driving the Sunda arc never paused. The Indo-Australian tectonic plate continued descending beneath the Eurasian plate at approximately 6 centimeters each year, which is about 2.4 inches each year. That steady motion had persisted for tens of millions of years, generating fresh magma through the same geological processes that had fed Krakatoa long before human history recorded its name. Molten rock continued gathering within the crust, following pathways shaped by immense pressure and persistent heat. Viewed from above, the caldera appeared settled into permanence. Viewed through geological time, it represented an interval between chapters. The empty basin preserved the memory of collapse, while gradually becoming the foundation for renewal. During the latter part of 1927, fishermen crossing the familiar waters noticed details that interrupted ordinary expectation. Thin columns of steam drifted across the sea. Patches of water carried unusual colors. Currents behaved differently above the center of the submerged caldera. Open ocean was beginning to display the earliest signs that another volcano had already started its ascent from the depths. The first sign appeared where no island belonged. Sailors crossing the familiar waters toward the close of December found a patch of sea interrupted by steam and dark fragments of fresh volcanic rock. The change seemed modest against the wide horizon, yet it marked the beginning of one of geology's rarest spectacles, the birth of an entirely new volcano within the scar left by its predecessor. On December 29th, 1927, 44 years and 4 months after the Great Eruption, a volcanic cone finally reached above the surface of the Sunda Strait. It emerged near the center of the submerged caldera, close to the northern volcanic cones that had vanished during the destruction of 1883. The newborn island consisted of loose black ash, fragmented lava, and intensely heated rock surrounded by clouds of steam, rising where magma met seawater. Every layer had formed through eruptions that were still unfolding beneath the waves, pushing material upward until the sea could no longer conceal it. Its arrival proved fleeting. Ocean swells attacked the fragile slopes almost immediately. Fresh volcanic deposits had not yet hardened into durable rock, leaving the cone vulnerable to relentless wave erosion. Within a single week, the island disappeared again, pulled apart grain by grain until only open water remained. The eruption had succeeded in reaching daylight, while the sea reclaimed the achievement with equal determination. The cycle repeated itself over the following months. Another cone rose into view, only to collapse beneath persistent waves. Fresh eruptions restored the summit, and the surrounding water dismantled it once more. Each appearance represented another contest between two natural forces working on very different timescales. Magma supplied new material from deep within the crust. The ocean removed whatever lacked the strength to endure. Neither process paused, and neither yielded quickly. Gradually, the balance shifted. Eruptions became productive enough that volcanic debris accumulated faster than waves could carry it away. Layer settled upon layer, each explosion adding another foundation for the next. By August of 1929, the cone remained above sea level without disappearing again. The island had reached a turning point where construction exceeded destruction, allowing the youngest land in the Sunda Strait to establish a lasting presence. Recognition soon followed. On August 11th, 1930, Indonesian authorities and scientists officially named the volcano Anak Krakatau, meaning child of Krakatoa. The name reflected more than geography. This island truly originated from the same volcanic system that had destroyed its parent, drawing molten rock through the same deep pathways while beginning an entirely new chapter above the water. Researchers immediately recognized the extraordinary opportunity before them. Volcanic islands are often discovered long after they have formed, their earliest stages already erased by time. Here, The process unfolded almost from its first visible moment. Scientists could document how eruptions built the cone, how waves reshaped its shoreline, how fresh lava gradually strengthened the island, and eventually how living organisms would arrive to occupy ground that had not existed before. Each eruption added another page to a geological record written in real time. Rather than studying fragments preserved from distant ages, observers watched an island assemble itself piece by piece. The caldera that once marked disappearance had become a cradle for creation, revealing that Earth's surface is never fixed, only passing through one form before another gradually takes its place. Once the young island secured its place above the sea, its story became one of steady construction. Each eruption added another layer. Each layer raised the summit a little farther into the sky. The landscape did not emerge through a single dramatic event. Growth arrived through thousands of repeated moments, each one leaving behind fresh lava, volcanic ash, and broken fragments of rock that gradually assembled an increasingly prominent cone. From 1930 onward, Anak Krakatau increased in height by an average of 7 to 9 meters each year, which is about 23 to 30 feet each year. The volcano achieved this remarkable pace through a style of activity known as strombolian eruption. Unlike the towering explosive columns associated with Plinian eruptions, strombolian activity consisted of frequent bursts that launched glowing lava, volcanic bombs, ash, and cinders into the air. Individual explosions often appeared moderate when viewed alone, yet their cumulative effect transformed the island decade after decade, producing a mountain through persistence instead of singular violence. Scientists recognized that they were observing an exceptionally rare natural process. Throughout the following decades, they repeatedly measured the island, recording changes in elevation, shoreline shape, and volcanic structure. Between 1930 and 2018, researchers completed 29 separate topographic surveys, eventually combining those observations into a continuous three-dimensional reconstruction of the volcano's development across almost 90 years. Few volcanoes anywhere on Earth have been documented with such consistency from the earliest stages of their existence. The cone continued expanding in every direction, while its summit climbed higher above the surrounding sea. Lava hardened into stronger foundations, allowing newer eruptions to build upon older deposits. Rain gradually carved channels into fresh volcanic slopes, while waves reshaped the coastline wherever loose material reached the water. Every natural process contributed another detail to an island that had not existed within living memory. By the 1990s, Anak Krakatau had become familiar to people living along the nearby shores of Java and Sumatra. On clear days, a thin column of ash or steam often marked its position on the horizon, revealing that construction remained active. Mariners passing through the Sunda Strait watched intermittent eruptions, much as previous generations had watched changing tides, accepting volcanic activity as part of the character of the passage connecting the surrounding seas. During the first decades of the 21st century, the island also attracted increasing numbers of visitors. Tourist boats approached the volcano during calmer periods, allowing passengers to photograph lava fountains rising from the summit after sunset. Guided excursions occasionally reached the lower slopes whenever local authorities judged conditions suitable. Travelers found themselves standing on one of the youngest islands on Earth, surrounded by terrain assembled almost entirely within the previous human lifetime. By the closing months of 2018, Anak Krakatau stood approximately 338 meters above sea level, which is about 1,100 109 feet. Its height approached that of New York City's Chrysler Building, an extraordinary achievement for land that had first broken the ocean's surface less than a century earlier. The volume of volcanic material accumulated during those decades exceeded anything the fishermen of 1927 could reasonably have imagined while observing the earliest plumes above open water. Detailed monitoring during the 2010s gradually revealed a subtle change in the volcano's form. Measurements showed that the southwestern flank was expanding more rapidly than other sides of the cone. Layer after layer accumulated along that sector, extending outward toward the edge of the older caldera wall. The island continued growing, although its shape was beginning to develop an imbalance that careful observation could no longer overlook. Many discoveries begin years after the events they ultimately explain. Information can exist in perfect clarity, preserved inside measurements collected with extraordinary precision, while its meaning remains overlooked until someone assembles every fragment into a single picture. That was the case for Anak Krakatau, whose changing shape had been recorded for years before anyone realized that the volcano had already begun a slow structural journey toward failure. In 2024, researchers at Pennsylvania State University published the results of an extensive investigation using satellite observations gathered between 2006 and 2018. Their study examined more than a decade of radar measurements collected during repeated passes over the volcano. Each orbit contributed another detailed snapshot, allowing the scientists to compare the island with its earlier form and measure changes, too subtle for human eyes to recognize from the ground. The technique behind the study is known as interferometric synthetic aperture radar. Instead of photographing the volcano in ordinary light, it compared returning radar signals from successive satellite observations. By analyzing tiny differences between those signals, researchers could determine whether parts of the landscape had shifted by only a few centimeters, which is about zero point 0.8 inches, or even by mere millimeters, which is about 0.04 inches. Across hundreds of observations, those minute changes accumulated into a remarkably detailed record of the volcano's long-term behavior. The results revealed a pattern that had remained concealed within the enormous collection of measurements. From at least 2006 onward, the southwestern flank of Anak Krakatau had been moving toward the sea. The motion occurred along a fault surface located approximately 850 meters below the volcano, which is about 2,789 feet below. Individual movements were extremely small, almost impossible to recognize without comparing years of observations together. Viewed across the entire record, however, the direction remained remarkably consistent. During the 12 years covered by the study, the fault experienced a cumulative displacement of approximately 15 meters, which is about 49 feet. The entire flank advanced little by little, each movement adding another fraction of distance to the total. Nothing suggested a rapid collapse. Instead, the volcano behaved like a structure, gradually adjusting under its own increasing weight, with every eruption placing additional material onto an already shifting foundation. The record also contained two intervals when that movement became noticeably faster. One occurred during the latter part of January in 2017. Another followed during June of 2018. Both periods coincided with stronger thermal emissions measured near the summit, indicating that fresh magma had entered the volcanic system. As molten rock forced its way upward, surrounding rock warmed and pressure changed within the cone. Those brief episodes appeared to encourage even greater movement along the unstable flank. Looking backward, through the completed dataset, the sequence appeared remarkably coherent. The signals preceding the later collapse already existed inside the satellite archive, faithfully preserved by instruments orbiting high above Earth. Monitoring systems operating at the time concentrated primarily on eruptive behavior, while gradual structural deformation attracted far less attention. The movement itself never disappeared. Its significance remained unrealized. The researchers concluded that this finding carries importance extending far beyond Anak Krakatau alone. If years of progressive flank movement can be recognized before a collapse occurs, then similar patterns may already exist within satellite records collected over other volcanic islands. The challenge now rests in identifying those subtle changes while they are still unfolding, allowing careful observation to accompany the steady growth of volcanoes long before their most consequential transformations begin. By the middle of 2018, Anak Krakatau entered a period of activity unlike anything documented during its modern lifetime. The volcano had spent decades building itself through frequent eruptions, yet the pace now increased noticeably. Instruments orbiting high above Earth began recording a dramatic rise in thermal energy, revealing that far more heat was reaching the surface than had become typical during previous years of observation. On June 30th, 2018, thermal measurements collected by the National Aeronautics and Space Administration using the moderate resolution imaging spectroradiometer instrument detected volcanic radiative power reaching roughly 100 times the volcano's long-term average. Fresh magma was arriving beneath the summit in greater quantities, feeding repeated explosions that continued week after week. Each eruption contributed another layer of lava, ash, and fragmented rock, steadily enlarging the volcanic cone that had already spent almost 90 years growing above the sea. From June through December, eruptive activity remained remarkably persistent. Strombolian explosions repeatedly launched incandescent lava high into the air, while intervals of stronger volcanic activity expelled denser clouds of ash and shattered rock. Lava descended the southwestern and western slopes, cooling into new layers that widened the volcano's profile. Ash plumes frequently climbed to heights approaching 5 kilometers, which is about 3.1 miles, above sea level before winds carried volcanic particles across the surrounding waters. The Sunda Strait continued functioning despite these displays, although the volcano increasingly demanded attention from everyone passing nearby. Ships reported thin layers of ash settling across their decks after drifting through the eruption clouds. Mariners adjusted routes whenever activity intensified, carefully navigating around floating pumice and drifting volcanic debris. From the coastlines of Java, the summit often glowed after sunset, its eruptive columns illuminated from below by fresh lava emerging from the crater. Government authorities in Indonesia responded by increasing the volcanic alert level as activity continued. The restrictions reflected the hazards posed by ash, volcanic bombs, and eruptive explosions surrounding the island. Exclusion zones kept visitors and vessels at safer distances while scientists maintained continuous observation. Every decision focused on managing the dangers that active eruptions commonly present. The volcano appeared to be behaving as an energetic but recognizable eruptive system. At the same time, another process continued beyond direct observation. Every explosion deposited fresh volcanic material onto the already expanding southwestern flank. Loose layers accumulated one above another, increasing the mass, pressing outward toward the older caldera margin. The gradual movement, identified years later through satellite analysis, continued beneath the growing cone, while successive eruptions added still more weight to a structure already experiencing slow deformation. Daily observations naturally emphasized the visible spectacle. Ash columns changed height. Lava flows advanced across fresh slopes. Explosions varied in frequency and intensity. Those dramatic features occupied the attention of monitoring networks because they represented the familiar language of an active volcano. The deeper structural adjustments unfolding inside the edifice remained far more difficult to recognize while eruptions dominated the landscape. By late December, the volcano had sustained this elevated activity for nearly 6 months. Persistent eruptions had become an accepted pattern rather than an extraordinary event. Scientists continued documenting each new explosion. Vessels continued navigating around exclusion zones, and nearby communities remained accustomed to seeing fresh ash rising over the horizon. On December 22nd, 2018, Anak Krakatau followed the same outward rhythm it had maintained throughout the preceding months. During the evening, at 3 minutes past 9 local time, the volcano entered a different chapter, one that no surface observation alone had fully anticipated. Time usually feels generous when measured against the pace of geology. Mountains rise over countless generations, coastlines shift through centuries, and volcanic islands spend decades assembling themselves one eruption at a time. Then there are moments when that immense clock seems to contract into a span shorter than a familiar conversation. During the evening of December 22nd, 2018, the history of Anak Krakatau changed within little more than a minute. At 3 minutes past 9 in the evening, local time, the volcano's southwestern flank gave way. Years of gradual movement reached a final threshold, and the unstable side of the cone began sliding toward the Sunda Strait. The collapse lasted approximately 70 seconds. During those 70 seconds, a volcanic structure that had spent almost 90 years growing above the sea lost a substantial portion of itself in one continuous motion. Scientists later estimated that between 0.22 and 0.27 cubic kilometers of volcanic material entered the water. That volume has often been compared with roughly 100 million fully loaded dump trucks, a comparison that helps translate geological scale into something more familiar without diminishing the extraordinary magnitude of the event. Ash, fractured lava, loose volcanic deposits, and older rock descended together as the volcano rapidly reshaped its own profile. A fisherman observing the event from nearby later described the island as appearing to split into two parts before the collapsing flank disappeared into the sea. The movement unfolded so quickly that the changing outline of the volcano became visible even from surrounding vessels. Decades of accumulated rock vanished from view almost as rapidly as they had entered it, leaving behind a dramatically altered summit. The collapse removed the upper portion of the cone with astonishing efficiency. Before the event, Anak Krakatau reached approximately 338 meters above sea level, which is about 1,109 feet. Afterward, the summit measured only about 110 meters, which is about 361 feet. Nearly two-thirds of the volcano's visible height disappeared during those brief moments, exposing a landscape that scarcely resembled the one documented only hours earlier. Although the structural failure transformed the volcano, it generated surprisingly little seismic energy. Instruments recorded vibrations comparable to an earthquake of approximately 3.4 magnitude. Such a signal remained well below the level expected to activate warning systems designed primarily to detect powerful tectonic earthquakes capable of producing tsunamis. From the perspective of those automated networks, the collapse lacked the characteristics normally associated with a major ocean-wide hazard. At Indonesia's Meteorological, Climatological, and Geophysical Agency Monitoring Center, no automatic tsunami alarm sounded. The instruments faithfully measured what they had been designed to recognize, yet the volcano had produced a different type of event. The principal danger came from an immense mass of rock entering the sea almost instantaneously, displacing an enormous volume of water rather than releasing energy through a large tectonic rupture. The nearest populated coastlines lay about 50 kilometers away, which is about 31 miles. From the collapse point, the newly generated wave expanded across the Sunda Strait in every direction, traveling with a speed comparable to that of a commercial passenger aircraft. Communities along the surrounding shores remained unaware that the landscape at the center of the strait had changed so dramatically. 24 minutes after the flank collapsed, at 27 minutes past 9 in the evening, the wave reached Tanjung Lesung Beach Resort. A performance by the Indonesian band 17 was underway as the water arrived, carrying with it the consequences of 70 seconds that had unfolded far beyond the horizon. Time can feel generous when measured on a clock, yet it becomes astonishingly brief when measured against the speed of the sea. Between the collapse of Anak Krakatau and the arrival of the first destructive waves along the nearest populated shores, only 24 minutes passed. Within that narrow interval rested every opportunity that could have altered the course of the evening. It was a span long enough for information to matter, yet far too brief for large-scale evacuation once the danger had already begun. Emergency planners often measure disasters in minutes instead of hours. 24 minutes cannot move entire coastal communities inland. Roads become crowded, decisions compete with disbelief, and distance quickly overwhelms the available time. A message arriving immediately after the collapse could still have drawn people away from beaches, harbors, and waterfront gathering places. Even a short movement toward higher ground or farther from the shoreline would have changed countless individual outcomes. No public warning arrived because the National Tsunami Warning System had been designed around a different chain of events. Its instruments and decision-making process focused primarily on tsunamis triggered by powerful tectonic earthquakes. Such earthquakes generate distinctive seismic signals that travel rapidly through the earth and can be recognized by monitoring networks within minutes. Once identified, those signals provide the foundation for automated warnings and emergency assessments. The collapse at Anak Krakatau followed another path entirely. A massive volcanic flank entered the sea, pushing water outward through sudden displacement instead of fault movement deep within the Earth's crust. The resulting seismic signature remained comparatively weak and lacked the characteristics expected from a major earthquake. Detection software searching for familiar earthquake patterns found little reason to activate emergency procedures. The ocean, however, responded to the collapsing mountainside regardless of what the instruments recognized. Conditions on the volcano itself made the situation even more difficult. Months of sustained eruptive activity had damaged monitoring equipment installed on the island. By the evening of the collapse, several important ground-based sensors were no longer providing the continuous observations scientists preferred. Information that might have revealed the final moments of structural failure was therefore incomplete, leaving researchers with only fragments to reconstruct after the event had ended. These circumstances combined into a chain of missed recognition. A warning system prepared for one class of tsunami encountered another. Damaged instruments reduced direct observations from the volcano. The landslide produced only modest shaking, equivalent to an earthquake of about magnitude 3.4, well below the level normally associated with destructive ocean waves. As a result, the tsunami advanced across approximately 50 kilometers, which is about 31 miles, of water before many people realized anything unusual had happened. Later investigations showed that the possibility of a volcanic flank collapse at Anak Krakatau had already appeared in scientific publications years before the disaster. Researchers had recognized the hazard as a realistic scenario. The tragedy revealed a different challenge entirely. Understanding that a threat exists does not automatically create the ability to recognize its arrival within minutes. Knowledge, monitoring, communication, and response must work together without delay. On that December evening, the gap between scientific awareness and operational readiness proved larger than the 24 minutes the coastline was given. For many people across the world, the disaster began with a recording that lasted only moments. A mobile phone held among a concert audience captured an ordinary evening at Tanjung Lesung. Music filled the stage, lights reflected across the shoreline, and nothing within the frame suggested that the landscape itself had already begun to change beyond the darkness. The collapse at Anak Krakatau had happened minutes earlier, far across the Sunda Strait, completely outside the view of everyone gathered there. As the performance continued, the ocean advanced from behind the stage. There was no retreat of the shoreline, no towering wall visible from a great distance, and no unmistakable signal that could have separated those final moments from every other seaside concert before them. The water reached the scaffolding with extraordinary speed. Metal supports folded, lighting towers fell, and performers, crew members, and members of the audience disappeared into the surge before the person holding the telephone lost control of the recording. The video reached social media while rescue operations were only beginning. Before daylight spread across Indonesia, millions of people had already watched the same sequence unfold. News organizations around the world replayed the recording because it revealed something that scientific papers, hazard maps, and technical diagrams had struggled to communicate. A volcanic landslide tsunami does not always announce itself with a powerful earthquake or an unmistakable warning. It can arrive during what appears to be an entirely ordinary evening, leaving almost no visible interval between normal life and overwhelming force. Behind every frame stood people whose lives extended far beyond the recording itself. The bassist, Muhammad Awal Purbani, was swept away. The road manager, Oki Wijaya, also lost his life. The drummer, the guitarist, and the singer's wife, Dylan Sahara, were among those carried away by the water. Families searched for relatives, while emergency workers continued moving through devastated coastal communities, where the same wave had crossed beaches, roads, homes, and resorts within only a few minutes. The following morning, the band's singer, Rifian Fajrsia, shared a message through social media describing the losses suffered by those closest to him. His words spread almost as rapidly as the video itself, giving names and faces to a tragedy that had first reached much of the world through distant images. Scientific discussions of volcanic hazards suddenly existed alongside personal grief, making the disaster impossible to understand only through measurements, satellite observations, or geological reconstruction. That connection remains one of the defining lessons of the event. The warning gap discussed by researchers is neither theoretical nor detached from everyday experience. It exists wherever information fails to arrive before the sea does. It can be measured in minutes, expressed through engineering reports, and reconstructed with remarkable scientific precision, yet it is ultimately experienced by ordinary people gathered for celebrations, work, travel, or family life along the shoreline. The recording from Tanjung Lesung became more than historical evidence. It transformed into a permanent reminder that advances in monitoring, communication, and hazard recognition are measured not only by improved instruments or more detailed models, but by whether future evenings along vulnerable coasts are allowed to continue uninterrupted when the Earth begins to move beyond the horizon. The collapse ended in little more than a minute, yet understanding it required years. After the events of December 22nd, 2018, researchers gathered every available satellite observation collected over Anak Krakatau, assembling an archive that stretched back more than a decade. Images, radar measurements, thermal records, and repeated orbital passes became pieces of a puzzle that no one had realized was already complete before the disaster unfolded. Among the most revealing records came from a method known as interferometric synthetic aperture radar. By comparing radar signals gathered during repeated satellite passes, scientists could detect movements of the ground measured in centimeters and sometimes even millimeters. The volcano had been observed again and again as satellites followed their ordinary routes around the Earth. Each pass stored another layer of information, preserving changes too gradual for the human eye and too subtle for conventional monitoring to recognize from the ground. When researchers completed their analysis, published during 2024, a remarkable pattern emerged. The southwestern flank of Anak Krakatau had not remained fixed in place during the years before the collapse. Between 2006 and 2018, that side of the volcano accumulated approximately 15 meters, which is about 49 feet, of gradual seaward movement. Every small shift appeared insignificant on its own. Together, they revealed an entire mountainside advancing toward failure over many years. The movement was far from uniform. Two intervals stood apart from the rest of the record. During late January of 2017, the pace of deformation increased noticeably. Another distinct acceleration appeared during June of 2018. Independent satellite observations measuring thermal emissions from the summit showed elevated volcanic heat during those same periods. Fresh magma entering the volcanic system likely increased internal pressure while warming the surrounding rock, conditions capable of reducing stability along the already moving flank. Viewed together, the records tell a story very different from one of sudden collapse without preparation. The final failure still occurred rapidly, yet the geological process leading toward it unfolded across many years. The evidence existed before the disaster, recorded automatically by satellites following routine observation schedules. Those measurements entered digital archives without attracting attention because no monitoring strategy had been designed to search specifically for this combination of long-term flank deformation and changing volcanic activity. That distinction reshaped scientific thinking after the disaster. The question no longer centered solely on reconstructing what had happened. Researchers instead began asking whether similar movement could be recognized while it was still developing. If gradual displacement can be measured years before collapse, then future instability may become visible long before the decisive moment arrives. Success depends less on inventing entirely new technology than on interpreting familiar observations in a different way. This perspective has become one of the principal directions guiding ongoing research. A study published during 2026 examined how Anak Krakatau has continued rebuilding since the collapse and emphasized the importance of tracking renewed flank movement throughout the volcano's present growth. The island continues adding fresh volcanic material with each eruption, rebuilding the cone layer by layer. Scientists now watch not only how high the volcano grows, but also how it moves, because the earliest signs of another future collapse may already be appearing, recorded once again by satellites passing overhead on ordinary journeys. Scientific understanding often changes through gradual refinement, yet there are moments when a single event redraws the boundaries of an entire field. The collapse of Anak Krakatau during 2018 became one of those moments. Researchers recognized that the disaster belonged to a broader family of volcanic processes extending far beyond the Sunda Strait. A growing volcanic island, perched along the edge of an older submarine caldera, could no longer be viewed as a stable structure unless its changing shape was measured as carefully as its eruptions. The combination of conditions documented at Anak Krakatau proved especially significant because none of them were unique. The volcano had expanded rapidly through repeated eruptions, adding fresh layers of ash, cinders, and lava before earlier deposits had fully strengthened. One flank accumulated material faster than the others, producing an increasingly uneven cone. Hydrothermal fluids circulated through fractures, altering minerals and weakening sections of volcanic rock. Beneath the growing island, the margin of the older caldera created a steep foundation where gravity continually encouraged outward movement. Together, these features formed a structural arrangement capable of developing in many volcanic settings across the world. Geologists soon compared those characteristics with islands scattered across distant oceans. Volcanic systems within the Canary Islands, the Azores, the Hawaiian Islands, and the Aleutian Islands all contain cones that have grown upon or near submerged volcanic depressions. Every volcano follows its own geological history, yet many share steep slopes, repeated eruptions, and layered deposits assembled over centuries or millennia. The comparison encouraged scientists to examine these landscapes through a broader lens, searching for subtle movement that might reveal instability long before visible collapse. Another lesson emerged from the timing of the disaster itself. Earlier theories had suggested that prolonged eruptive activity could increase structural risk by steadily loading one side of a volcano with additional material. Anak Krakatau provided one of the clearest documented examples supporting that idea. Months of vigorous eruption deposited fresh lava and fragmented rock onto an already moving flank. Each eruption contributed another layer, increasing weight, while internal heat and magma intrusion continued influencing the weakened structure. The period that appeared most productive in terms of volcanic growth also marked the interval when collapse became increasingly likely. Research published after 2018 reflected this shift in perspective. Scientists proposed monitoring systems that combined repeated satellite radar observations with thermal measurements, topographic mapping, and continuous deformation analysis. Instead of treating these information streams as separate records, many studies argued for integrating them into unified hazard assessments capable of identifying dangerous trends while they remained gradual. The emphasis moved toward recognizing patterns developing across months and years, instead of focusing only upon sudden eruptive changes. The experience also clarified an important distinction within volcanic science. Earlier publications, including studies released during 2012, had already identified the southwestern flank of Anak Krakatau as a location deserving attention. The scientific concern itself proved well-founded. The greater weakness lay elsewhere, within the practical systems responsible for converting research into operational monitoring and public warning. Knowledge had advanced farther than the infrastructure designed to apply it. That realization continues shaping volcanology today. The legacy of Anak Krakatau reaches beyond one island or one tragic evening. It endures in a growing commitment to observe volcanoes as evolving structures whose motion, form, heat, and internal changes belong to the same continuing story, One measured patiently before the landscape decides to change all at once. Nothing about the island suggested an ending. The collapse had removed much of the cone above the sea, yet the volcanic system beneath remained active, connected to the same rising magma that had spent decades constructing the island. Within hours, the newly exposed conduit encountered seawater directly. That meeting transformed the style of the eruption. Superheated magma flashed surrounding water into expanding steam, driving repeated hydrovolcanic explosions that hurled ash, fragmented rock, and dense clouds high above the crater. The landscape had changed dramatically, although the engine powering it continued without interruption. Those first weeks revealed how rapidly volcanic construction could resume. By the 10th of January, 2019, only 19 days after the collapse, drone surveys documented an extraordinary recovery. Fresh pyroclastic deposits had already restored approximately 84% of the island's remaining above sea volume. Layer after layer accumulated across the scar left by the landslide, replacing absence with newly erupted material. Scientists had expected rebuilding to occur, yet the pace exceeded many early estimates and demonstrated the remarkable productivity of the volcanic system. One explanation gradually emerged from continued observation. The missing southwestern flank had represented an enormous load pressing against the volcanic conduit and surrounding rock. Once that mass disappeared into the Sunda Strait, internal pathways experienced less resistance. Magma continued rising through fractures that remained open, feeding sustained eruptions instead of entering a prolonged dormant period. The collapse had reshaped the volcano, though it had not exhausted the source supplying molten rock from below. Throughout 2019 and 2020, the island alternated between contrasting phases of activity. Periods of energetic hydrovolcanic explosions accompanied direct interaction between seawater and magma, filling the air with ash and steam. These episodes gradually gave way to intervals dominated by quieter cone building as fresh lava and fragmented volcanic debris accumulated around the vent. Each cycle modified the outline of the island, smoothing some surfaces while creating new slopes elsewhere. By the beginning of 2021, the summit had risen to approximately 150 meters, which is about 492 feet. As rebuilding continued, the eruptive character evolved once again. During 2022, persistent strombolian activity returned as the dominant pattern. Repeated bursts launched glowing fragments into the air, while lava continued, adding new layers around the central cone. Observers recognized the familiar rhythm because it closely resembled the style that had shaped Anak Krakatau during the decades preceding the collapse. The volcano had entered another stage of growth, guided by processes that had defined much of its modern history. By 2026, the summit reached approximately 189 meters, which is about 620 feet above sea level. That elevation remains far below the height achieved before the collapse, yet the island continues adding material through ongoing eruptions. Each deposit contributes another chapter to a landscape still under construction. Indonesian authorities have maintained alert levels between Level 2 and Level 3, while enforcing a maritime exclusion zone extending from 2 kilometers, which is about 1.2 miles, to 5 kilometers, which is about 3.1 miles, around the volcano. The child born from destruction continues rebuilding itself, following the same enduring geological rhythm that first carried its summit above the sea. A volcano remembers through its architecture. Every eruption lays another layer across those that came before, preserving a physical record beneath the surface even as the visible landscape changes. Years after the collapse of 2018, researchers assembled the most detailed portrait ever created of Anak Krakatau's development. Their work drew together 29 historical topographic surveys, satellite observations, drone mapping, and field measurements collected across decades. The result extended beyond a description of the island's past. It offered a careful projection of how the growing cone may continue evolving if the same geological processes remain active. The reconstruction revealed a pattern that carried profound importance. Although the collapse had dramatically reshaped the volcano, the rebuilding process followed many of the same pathways that had operated before the failure. Fresh eruptions repeatedly added loose volcanic deposits across the cone, while earlier lava flows gradually hardened beneath them. Each new layer became part of an increasingly complex structure in which materials of different strength rested against one another. The island was rebuilding its height, though it was also rebuilding the internal arrangement that had once contributed to instability. Particular attention focused upon the boundary separating older lava from younger accumulations of volcanic ash, fragmented rock, and consolidated tuff. Investigations of the 2018 collapse indicated that this contact formed the principal surface along which failure eventually occurred. The new analysis showed that each successive eruptive cycle was establishing a comparable boundary once again. Time had erased the visible scar across the volcano, yet similar geological relationships were gradually returning within the growing edifice. Measurements also demonstrated that growth remained uneven. The southwestern flank continued receiving a greater share of erupted material than other parts of the island, preserving the same asymmetrical geometry identified before the collapse. Every eruption contributed additional weight to one side of the cone, while extending the slope farther outward. Such differences developed gradually across years, instead of appearing after any single eruption, making careful, long-term observation essential for recognizing meaningful change. Another process continued working beyond direct view. Rainwater and seawater entered fractures throughout the volcanic rock before circulating through regions heated by magma below. As these fluids moved through the edifice, they altered minerals and reduced the strength of portions of the rock over extended periods. This hydrothermal alteration affected the ability of volcanic deposits to remain firmly bonded together, particularly where fractured layers already existed. The volcano therefore evolved through a combination of construction and gradual internal weakening occurring at the same time. The conclusions presented in the 2026 study remained measured in tone, yet they carried unmistakable significance. Researchers explained that as Anak Krakatau approaches the slope angles that existed before the previous collapse, monitoring deformation across the growing flank becomes increasingly important. The objective is no longer limited to documenting eruptions after they occur. Equal attention must be given to detecting gradual movement while it remains small enough to measure. For that reason, the study identifies satellite radar interferometry and global positioning system monitoring as essential tools for the years ahead. Together, they can reveal shifts measured in centimeters or even smaller amounts before visible changes appear across the landscape. The message emerging from the rebuilt volcano is steady and unmistakable. The same structure is taking shape again, and this time the opportunity exists to observe its changing form before the next decisive movement unfolds. Every warning begins with a race that cannot be negotiated. Once a large section of a volcanic island enters the sea, the resulting wave follows the rules of water, gravity, and distance with unwavering consistency. No improvement in communications, computing, or observation can persuade those physical laws to slow their pace. They determine the interval available for action before the first surge reaches land, and that interval remains fixed regardless of human preparation. For Anak Krakatau, the nearest densely populated coastlines lie about 50 kilometers away, which is about 31 miles. A tsunami, generated by another major flank collapse, would typically cross the Sunda Strait in roughly 20 to 30 minutes, depending upon local water depth and the exact source of the collapse. Those precious minutes already include the wave's journey. Any warning must fit entirely inside the remaining fraction of that brief span. Several events must unfold before a message can reach people standing along the shoreline. Instruments must first recognize that a collapse has occurred. The incoming information must then be processed, interpreted correctly, and identified as an event capable of generating a tsunami. Officials must authorize and distribute an alert through established communication networks. Finally, the warning must reach coastal communities, and people must have enough time to move away from the water's edge before the wave arrives. Each stage consumes moments that cannot be recovered once they have passed. During the disaster of 2018, the sequence faltered at its opening step. The collapse itself did not produce the kind of seismic signal expected from a large tectonic earthquake. Because the landslide entered the sea without creating a powerful earthquake signature, the event escaped immediate recognition as the source of a dangerous tsunami. Valuable minutes continued slipping away while the wave had already begun traveling outward across the strait. Since that tragedy, Indonesia has strengthened its monitoring network through several complementary systems. Additional tide gauges now measure changing sea levels at more locations. Ocean pressure sensors connected through submarine cables provide faster observations from the surrounding waters. Acoustic monitoring systems add another layer of information, while expanded satellite radar interferometry allows scientists to track gradual deformation of volcanic slopes with greater precision than before. Together, these improvements create a broader picture of the volcano and the surrounding sea than existed before the collapse. Researchers remain careful when describing what these advances can accomplish. Better monitoring reduces uncertainty, increases the likelihood of recognizing dangerous changes sooner, and shortens the delay between detection and official response. Even so, the distance between Anak Krakatau and nearby coastlines leaves very little room for delay. Physics continues defining the available interval, while technology works only within the boundaries established by that interval. The most meaningful improvement, therefore, lies in making full use of the time that truly exists. Every second saved during detection, analysis, communication, and public response increases the chance that more people can move beyond the reach of the incoming water. The window itself remains unchanged, measured by geography and wave speed. Human effort cannot widen it, although thoughtful preparation can help ensure that fewer moments are lost before the warning begins its own journey toward shore. Every day, vessels from many nations cross the Sunda Strait with little indication that they are passing through one of Earth's most dynamic volcanic landscapes. Cargo ships, ferries, fishing boats, and tankers follow established routes between the Indian Ocean and the Java Sea, weaving through waters that have shaped trade for centuries. The volcano rising from the center of the strait occupies only a small part of that wider passage, while the surrounding corridor supports movement that reaches far beyond Indonesia itself. The Sunda Strait is far from an isolated channel. It forms one of the principal maritime links between the Indian Ocean and Southeast Asia, serving as an important alternative whenever traffic through the Strait of Malacca becomes constrained. A substantial share of seaborne commerce moving between Europe, the Middle East, and East Asia passes through Indonesian waters, placing this region within one of the busiest transportation networks on the planet. Every voyage depends upon coastlines that remain open, navigable, and resilient despite the geological forces that continue shaping them. Communities surrounding the strait have grown alongside these waters for generations. Western Java and southern Sumatra together support populations numbering in the tens of millions. Cities, market towns, fishing villages, industrial ports, and beach resorts occupy long stretches of shoreline, with many neighborhoods standing only a few meters above sea level, which is about 10 feet. Their daily routines are closely tied to the sea through transportation, tourism, commerce, and fishing, creating a landscape where human activity and coastal geography remain closely intertwined. When the tsunami of 2018 spread outward from Anak Krakatau, its effects unfolded across more than 300 kilometers of coastline, which is about 186 miles. The wave reached beaches, harbors, residential districts, tourist destinations, and working waterfronts within the same broad sweep. Damage appeared across a continuous coastal arc instead of remaining confined to one isolated location. Roads were broken apart, port facilities suffered extensive losses, and communities separated by considerable distances found themselves facing the same disaster within a remarkably short period. The consequences extended well beyond the first hours after landfall. Tourism, which had become an increasingly important source of income throughout the region, declined sharply as visitors canceled reservations and coastal businesses struggled to recover. Commercial fishing fleets lost equipment and infrastructure. Transportation networks required extensive repairs before regular movement could resume. Economic disruption spread through supply chains that connected local communities with regional and international markets, demonstrating that the influence of a volcanic island can extend far beyond its visible shoreline. Development has continued since then. New buildings, expanding neighborhoods, and growing commercial activity have added even greater value to the surrounding coastline. As populations increase and infrastructure becomes more extensive, the number of people and critical facilities exposed to coastal hazards also grows. This changing landscape means that the significance of Anak Krakatau cannot be measured solely by the dimensions of the volcano itself. Its setting within one of the world's most active maritime corridors gives every change in the island broader importance. The same strait that carries commerce between continents also carries the memory of how closely geological processes and human civilization remain connected, sharing the same waters day after day beneath an ever-changing horizon. Within days of the tsunami, familiar routines began returning to the shores of Western Java. Debris was gathered into piles. Damaged fishing boats were lifted back toward the water, and temporary shelters gradually gave way to repaired homes and reopened businesses. The coastline still carried visible reminders of the disaster, yet daily life continued to reclaim the same ground. Families rebuilt where they had always lived, following a pattern repeated across generations whenever the sea and the volcano altered the landscape. Many observers from distant places imagine relocation as the obvious solution after such a tragedy. The reality along the Sunda Strait is shaped by circumstances that extend far beyond the memory of a single disaster. Fishing communities depend upon immediate access to the sea before sunrise each day. Tourism workers earn their living where visitors gather along the beaches. Port employees, merchants, transport operators, and countless small businesses all rely upon the movement of people and goods through coastal settlements. Leaving permanently would also mean leaving occupations, family networks, schools, and social ties that cannot be recreated elsewhere with ease. Farmers face a similar choice. The volcanic landscapes surrounding Western Java have received repeated layers of mineral-rich ash over many centuries. Those deposits have produced some of the most fertile agricultural soils in Southeast Asia, supporting rice fields, fruit orchards, vegetable farms, and plantations that provide food and income for millions. Fertility born from volcanic activity has long encouraged settlement near landscapes that also possess the capacity for sudden destruction. The same processes that build productive land also preserve the possibility of future eruptions and coastal hazards. The surrounding sea offers another source of enduring opportunity. Waters flowing through the Sunda Strait sustain productive fisheries that contribute significantly to regional food supplies and local economies. Generations of experience have taught fishing families where currents gather marine life and when seasonal changes bring the best harvests. Their knowledge is rooted in daily observation, inherited skills, and relationships with the sea that cannot easily be transferred to distant inland communities. For many households, remaining close to the shoreline represents the only practical path toward economic stability. This pattern reaches far beyond Indonesia. People continue living beside active volcanoes, major rivers, earthquake faults, and hurricane coastlines across the world because those places also provide fertile land, transportation routes, fresh water, employment, and cultural identity. Human settlement has always balanced opportunity with uncertainty. The calculation is rarely made without awareness of danger. More often, it reflects the immediate necessities of work, family, and survival, measured against hazards that may arrive only rarely during a lifetime. Knowledge by itself seldom changes that balance. Most coastal residents understand that the sea can become dangerous under extraordinary circumstances. Information has value, yet information alone cannot replace employment, restore farmland, or create new communities overnight. Decisions about where to live emerge from practical realities as much as scientific understanding. This is where warning systems become especially significant. They do not ask entire populations to abandon productive landscapes that have supported them for generations. Their purpose is far more focused. They seek to preserve the lives of people who have chosen, or have needed, to remain. Between the volcano and the shoreline, every improvement in detection, communication, and preparedness strengthens that possibility, allowing communities to continue drawing their future from the same waters and fertile ground that have sustained them for centuries. Long before researchers could ask what the newest collapse meant for future hazards, another record had already been unfolding across the islands surrounding Anak Krakatau. It began after the eruption of 1883 erased nearly every trace of life from the nearby landscape, where forests had once stood. Only fresh volcanic surfaces remained. Those neighboring islands, Rakata, Sertung, and Panjang, became one of the rare places on Earth where the return of an entire ecosystem could be observed from its earliest steps. The first arrivals came without ships or human assistance. Blue-green algae spread across volcanic ash, drawing together loose particles into the beginnings of soil. Fern spores drifted through the air and settled into tiny fractures where enough moisture collected to support new growth. Spiders crossed open water by releasing delicate strands that caught the wind, allowing them to descend onto land that contained almost nothing capable of sustaining life only a short time earlier. Each arrival altered the environment in subtle ways, making the next arrival slightly more likely. Scientists returned repeatedly to document those changes. By 1886, only 3 years after the eruption, 26 plant species had already established themselves. During the following decade, grasses expanded across broad patches of ground, helping stabilize the developing soil. Insects multiplied as vegetation became more diverse, creating food for birds arriving from neighboring islands and the nearby coasts of Java and Sumatra. Every season added another layer to a living archive, revealing how communities assemble themselves when nature begins almost from nothing. When Anak Krakatau emerged above the sea in 1930, the experiment gained a remarkable new chapter. An entirely new volcanic island now stood beside older islands whose ecological histories had already been observed for decades. Scientists could compare different stages of recovery within the same archipelago, watching seeds, insects, reptiles, birds, and other organisms establish themselves on land whose exact birthday was already known. Very few places on Earth have offered such an uninterrupted opportunity to witness ecological succession from the first exposed rock onward. The collapse of 2018 reshaped that opportunity once again. Fresh lava and volcanic deposits replaced areas where vegetation had already taken hold, exposing raw surfaces across parts of the island. Researchers soon documented pioneer organisms returning to those newly formed landscapes. Spores, microorganisms, and hardy plants resumed work that had unfolded before, beginning another cycle of soil formation and biological expansion. The process did not restart across the entire archipelago, only across the terrain that the collapse and subsequent eruptions had created, allowing several ecological timelines to exist side by side. Today, the Krakatoa Island Group contains communities that have developed through nearly a century of continuous scientific observation. Some habitats trace their origins to the years following 1883. Others began with the birth of Anak Krakatau in 1930. Still others emerged after the reshaping of the island during 2018. Together they form an ecological mosaic unlike any other, revealing how life repeatedly responds to destruction with patient accumulation. Even as volcanologists measure deformation, eruption rates, and structural stability, ecologists continue recording another story, one where every new layer of volcanic rock becomes the foundation for another generation of living landscapes. Few places have reshaped as many branches of science as the Krakatoa volcanic system. Each eruption altered the landscape, yet every transformation also opened another opportunity for observation. Across generations, researchers from different disciplines found themselves studying the same islands for entirely different reasons. Geologists mapped fresh volcanic layers, ecologists recorded returning forests. Marine biologists explored changing seafloors. Together, their work transformed a small archipelago into one of the most influential natural laboratories on Earth. The ecological records begun after the eruption of 1883 became especially valuable because they captured life returning from its earliest stages. The surviving islands of Rakata, Sertung, and Panjang allowed scientists to document ecological succession with unusual precision. Species arrived one after another, each changing the conditions for those that followed. Those observations became central examples within the study of island biogeography, helping explain how isolated land acquires increasing biological complexity through immigration, competition, adaptation, and gradual environmental change. Patterns that often unfold across thousands of years could be observed here within the span of human lifetimes. Ideas first proposed by Charles Darwin concerning natural selection also gained an exceptional testing ground among these volcanic islands. Organisms reaching fresh terrain encountered unfamiliar conditions, limited resources, and new ecological relationships. Plants spread into different elevations, insects occupied expanding habitats, and birds established breeding populations as food became more abundant. Evolution itself still required many generations, yet the ecological foundations supporting evolutionary change emerged rapidly enough to be documented directly. Researchers could follow the sequence of colonization almost year by year, building one of the clearest records of ecosystem assembly ever compiled. Beyond the shorelines, the submerged caldera revealed another scientific frontier. Steep volcanic walls descended into thermally active waters where dissolved minerals altered the chemistry of the surrounding sea. Marine organisms, adapted to these distinctive environments, formed biological communities, unlike those found elsewhere within the Sunda Strait. These underwater habitats offered valuable comparisons with other hydrothermal systems around the world, helping researchers understand how life responds to chemically unusual environments shaped by continuing volcanic activity. The collapse during 2018 extended the scientific influence of Anak Krakatau into another field that continues expanding today. Detailed satellite observations, numerical simulations, and geological reconstruction produced one of the most comprehensive modern studies of volcanic landslide tsunamis ever assembled. Researchers refined methods for interpreting ground deformation, recognizing structural instability, and evaluating how growing volcanic islands evolve toward failure. The lessons drawn from this single event soon informed hazard assessments far beyond Indonesia, guiding investigations at volcanic islands across both the Atlantic Ocean and the Pacific Ocean, where similar combinations of unstable slopes and active eruptions exist. The value of Anak Krakatau, therefore, reaches well beyond its shoreline. Every generation has inherited a different island, shaped by eruption, collapse, rebuilding, and renewal, while the scientific record has remained remarkably continuous. Discoveries made here have strengthened ecology, evolutionary biology, marine science, volcanology, and natural hazard research without belonging entirely to any one discipline. The volcano continues building new rock above the sea, while each transformation adds another chapter to a body of knowledge that has grown almost as steadily as the island itself. The outline of Anak Krakatau appears permanent when viewed across a human lifetime, yet the rocks beneath it tell a far longer story. Far below the present cone lies a volcanic system that has been reshaping itself for at least 360,000 years. Each generation has witnessed only a brief moment within that history. The island standing above the sea today is another expression of a process that began long before any written record, following rhythms measured across centuries and millennia instead of individual lives. Geologists describe Krakatoa as a resurgent caldera system. Such systems do not follow a single path toward growth before reaching a stable ending. They pass through repeating phases. Magma gathers within the crust until enormous eruptions empty part of the underground reservoir. The unsupported ground above then subsides, creating a broad volcanic depression known as a caldera. Heat and molten rock continue rising afterward, feeding fresh eruptions that gradually construct another volcanic edifice within or along the margins of the older collapse. The cycle resumes with each new generation of volcanic activity. Evidence preserved in lava layers, volcanic ash, and submarine deposits indicates that this location has experienced at least 4 major caldera forming eruptions before modern observation began. Every one transformed the surrounding landscape. Coastlines shifted. New islands emerged while older land disappeared beneath the sea. Marine environments adjusted to changing depths, and fresh volcanic slopes replaced those that had collapsed. None of these events marked an ending. Each became another chapter within an ongoing sequence that continued rebuilding almost as soon as destruction had finished. The eruption of 1883 occupies a unique place because it became the first complete caldera forming event documented with modern scientific methods. Observers recorded ash clouds, atmospheric effects, ocean disturbances, and the gradual appearance of new land during the decades that followed. Even so, the eruption represented another recurrence of a pattern already repeated many times before. It stands out because people witnessed it in extraordinary detail, while its predecessors remain preserved mainly within geological evidence. Anak Krakatau belongs to the rebuilding stage that followed that eruption. Whether researchers count it as the fifth, sixth, or seventh major volcanic edifice depends upon how fragmented portions of the older record are interpreted, yet the exact number changes little about the broader narrative. Molten rock found another path upward. Successive eruptions accumulated fresh lava and volcanic fragments, and the island gradually reclaimed space above sea level. Growth continued until structural weakness developed within one flank, leading to the partial collapse during 2018. That event interrupted the cone without resetting the entire caldera, allowing renewed eruptions to rebuild almost immediately. Viewed across the immense span of the caldera's history, the interval separating 1883 from 2018 occupies only a brief portion of the current volcanic episode. The system has remained active throughout, constructing, adjusting, collapsing in part, and continuing its ascent. The cone visible today is neither the first expression of this enduring engine nor its final form. It rises from foundations shaped by countless earlier cycles, carrying forward a geological conversation that began hundreds of thousands of years ago and continues one eruption, one collapse, and one renewal at a time. Far beneath the islands, beyond the reach of earthquakes that people can feel, and volcanoes that rise above the sea, an immense movement continues without pause. It has no beginning within human memory and no foreseeable end. Every eruption, every caldera collapse, every layer of fertile volcanic soil spread across western Java, every island that has appeared and disappeared within the Sunda Strait, traces back to this single planetary engine operating far below the surface. In this region, the Indo-Australian tectonic plate descends beneath the Eurasian tectonic plate at a rate of about 6 centimeters each year. That pace has remained remarkably consistent for tens of millions of years and is expected to continue for tens of millions more. Human civilizations rise and disappear while the plates advance only a few kilometers, which is about 1.9 miles. From the perspective of the Earth itself, history unfolds while the crust shifts almost imperceptibly. As the descending slab reaches depths of approximately 100 kilometers, which is about 62 miles, pressure and temperature transform the minerals locked within it. Water and dissolved gases are released into the overlying mantle. Those materials reduce the melting point of the surrounding rock, allowing magma to form where solid mantle would otherwise remain intact. The newly generated magma becomes less dense than the rocks around it and begins its gradual ascent through fractures within the crust. Some pockets cool before reaching the surface. Others continue upward until they feed volcanic chambers waiting beneath mountains and islands. Nothing about this mechanism is responding to climate change, industrial activity, or any other influence created by humanity. The heat driving it originates within the planet itself, sustained by conditions established during Earth's formation, and by the continuing decay of naturally occurring radioactive elements inside the mantle and crust. Plate tectonics provides the motion, while planetary heat supplies the energy. Together, they produce a cycle that has continued across intervals so immense that entire languages, kingdoms, and civilizations occupy only brief moments within it. Krakatoa represents one visible expression of that process, although it is only one among many. About 1,400 kilometers, that is nearly 870 miles, farther east along the same volcanic arc, stands Tambora. Its eruption during 1815 injected enormous quantities of ash and sulfur-rich gases into the atmosphere, reducing global temperatures and contributing to the period remembered as the year without a summer. Crop failures spread across the northern hemisphere, and widespread famine followed in many regions as harvests declined beneath altered skies. Roughly 400 kilometers, which is about 249 miles, to the northwest lies Toba, another volcanic center created by the same descending plate. Around 74,000 years ago, Toba produced one of the largest known eruptions in the history of our species. Ash covered enormous areas, atmospheric conditions shifted across continents, and some researchers suggest the resulting environmental stress may have reduced the global human population to only a few thousand individuals, although the extent of that decline continues to be studied and debated. Seen together, Krakatoa, Tambora, and Toba are not isolated hazards scattered across Indonesia. They are neighboring expressions of one continuous subduction system, each revealing a different scale of the same enduring conversation between the descending plate, the rising magma, and the restless interior of the Earth. Knowledge has advanced with remarkable speed since the collapse, yet one boundary remains unchanged. It does not arise from a lack of careful observation or dedicated research. It comes from the difference between understanding a natural system and controlling the moment when that system decides to move. Anak Krakatau has become one of the most closely studied volcanic islands on Earth, while preserving a measure of uncertainty that every scientific paper continues to acknowledge with careful restraint. Researchers can now reconstruct the mechanics of a flank collapse with impressive detail. Computer models estimate how much rock must fail before a tsunami forms, how rapidly displaced seawater expands into outward moving waves, which stretches of coastline receive the greatest energy, and how long those waves require to travel across the Sunda Strait. Modern simulations are continually refined using measurements collected after the events of 2018, allowing scientists to compare predicted behavior with observations gathered from satellites, drones, field surveys, and coastal records. Observation has also entered a different era. Additional monitoring instruments now surround the volcano and the neighboring waters. Radar satellites repeatedly measure minute changes in the shape of the volcanic cone. Drone flights create detailed surface maps after eruptive episodes. Tide gauges, pressure sensors linked by submarine cables, and acoustic monitoring systems provide streams of information that were unavailable before the disaster. Together, these tools reveal changes that would once have remained unnoticed until they became obvious at the surface. Looking backward has proven equally valuable. Scientists examining measurements collected before the collapse have identified patterns that now receive much closer attention. Progressive deformation of the southwestern flank, repeated inflation and deflation associated with magma movement, continued accumulation of loose volcanic deposits, and chemical weakening caused by circulating hot fluids all appear as pieces of a larger sequence. Those observations have shaped monitoring strategies designed to recognize comparable developments during the present rebuilding phase, giving researchers a clearer picture of how instability gradually emerges. Even so, one crucial question remains beyond present capability. No instrument can determine the exact day when gravity will overcome the strength of fractured volcanic rock. No satellite can identify the precise week when accumulated stress reaches its final threshold. A volcano may display familiar warning signals for years without major structural failure, while another may change rapidly within a much shorter interval. The governing processes involve countless interacting variables, many concealed deep within the edifice, where direct observation remains impossible. Distance imposes another limit that technology cannot erase. The nearest populated shores lie close enough that a tsunami generated by a major collapse can arrive in roughly 24 minutes. Better monitoring does not lengthen that interval. Improved instruments cannot slow the speed at which waves cross the strait. They can only reduce the time required to recognize the event, confirm its significance, distribute official warnings, and begin protective action before the water reaches land. For that reason, the central effort surrounding Anak Krakatau has become one of efficiency rather than certainty. Every refinement seeks to preserve more of those same 24 minutes than were available during the tragedy of 2018. The science continues to grow more capable, while the clock set by geography and physics remains exactly where it has always been. Each day, long before anyone steps onto a research vessel or reviews a scientific report, streams of information begin arriving from the Sunda Strait. They come from instruments that never sleep, each measuring one small part of a volcanic system that continues to rebuild itself. Together, they form a watch that extends across land, sea, and space, following the rhythm of Anak Krakatau as it grows through another chapter of its long history. Seismometers listen to vibrations traveling through the volcano. They distinguish brittle rock fracturing from the deeper rumble produced as magma moves through cracks and conduits below the surface. Every tremor carries information about changing conditions inside the edifice. A single signal rarely provides a complete explanation. Yet, thousands of recordings collected over weeks and months reveal patterns that help volcanologists recognize shifts in the behavior of the system before they become visible above ground. Measurements of shape are equally important. Global positioning system receivers installed on nearby islands, together with instruments placed on the surrounding seafloor, detect movement measured in centimeters. The volcanic cone expands as magma accumulates beneath it and contracts after pressure is released through eruptions. Those gradual changes create a record of deformation that can be compared with seismic activity, allowing separate observations to strengthen one another instead of standing alone. Across the surrounding waters, tide gauges and ocean pressure sensors maintain another layer of observation. Their purpose is straightforward. They watch for changes in sea level that could indicate the beginning of a tsunami generated within the strait. These instruments cannot prevent a wave from forming, although they can provide confirmation that unusual movement has already begun. Every minute saved between detection and official warning carries practical value for communities located along nearby coastlines. High above the Earth, radar satellites complete another circuit of observation. Their repeated orbital passes allow scientists to compare successive images and measure minute changes across the volcanic surface using interferometric synthetic aperture radar. Data that once waited for later examination now enters processing systems with far greater speed, allowing deformation maps to be produced while conditions are still developing instead of long after an eruptive episode has ended. During the present year, the official alert level continues to fluctuate between level 2 and level 3, while the maritime exclusion zone remains between 2 kilometers, which is about 1.2 miles, and 5 kilometers, which is about 3.1 miles, from the island. Strombolian eruptions continue to send ash columns several kilometers into the sky, with plumes commonly reaching between 2 kilometers, which is about 1.2 miles, and 3 kilometers, that is nearly 2 miles. At night, bursts of glowing lava remain visible from portions of the western Java coastline. The southwestern flank also continues adding new material, gradually rebuilding the same side that failed during the collapse. Scientists studying these observations now recognize combinations of signals that carried greater meaning than anyone fully appreciated before 2018. Accelerating flank movement, rising surface temperatures, accompanying stronger eruptions, and changes in eruptive style associated with fresh magma entering the system all receive careful attention. Even so, no sequence guarantees that collapse will follow, and no absence of those signals guarantees stability. The watch has become more capable, the measurements more complete, and the understanding far deeper. Whether nature will reveal its intentions early enough for every observation to become timely action remains a question that no instrument can answer on its own. Across the shores facing the Sunda Strait, the rhythm of ordinary life continues with remarkable consistency. Fishing boats leave before dawn, ferries cross between islands, markets open beside the waterfront, while homes, schools, ports, and hotels stand close to the sea. Taken together, these coastlines are home to more than 65 million people spread across western Java and southern Sumatra in one of the most densely inhabited coastal regions anywhere on Earth. The number continues to increase as expanding communities occupy land where the meeting of ocean and volcano has shaped daily existence for generations. Population growth has gradually transformed the consequences of future events. A shoreline that supported fewer residents several decades ago now contains larger towns, wider transportation networks, additional industrial facilities, and expanding tourist destinations. Each new neighborhood adds another layer to an already complex landscape. Development has brought economic opportunity, stronger regional connections, and improved infrastructure, while also placing more people within reach of hazards that have remained part of the geological setting throughout recorded history. Researchers have examined what could happen if another substantial section of Anak Krakatau's southwestern flank were to fail. Computer simulations indicate that a collapse involving approximately 0.28 cubic kilometers of rock could produce an initial wave reaching about 43 meters, which is about 141 feet, near the point of failure. The surrounding islands would experience the first arrival in less than 1 minute. From there, the energy would continue across the Sunda Strait, with hazardous waves approaching sections of the Java and Sumatra coast during roughly the same 24-minute interval identified through studies of the 2018 event. Every additional increase in collapse volume changes the outcome. Larger failures displace more seawater, allowing greater wave heights to develop before they spread outward across the strait. Coastline shape, underwater topography, and local bathymetry influence the height eventually experienced at each location, meaning neighboring communities may encounter very different conditions despite sharing the same source. Scientists, therefore, model many possible scenarios instead of relying upon a single prediction, recognizing that each variation provides another piece of understanding for emergency planning. Evidence collected over many decades leaves little uncertainty regarding the existence of this hazard. Geological deposits preserve records of earlier tsunamis. Historical observations document the events of 1883 and 2018. Modern satellite measurements reveal the volcano rebuilding the same unstable flank once more. Computer models describe how waves travel after collapse, while monitoring networks measure the volcano almost continuously. Separate lines of investigation converge toward the same conclusion, each strengthening the confidence placed in the others. Even with this growing body of knowledge, certainty has natural limits. Science can estimate the consequences of specific collapse sizes, identify sectors of the volcano that deserve careful attention, and calculate how rapidly waves would move through the strait. Those achievements make preparation more effective than it was in earlier generations. They do not transform a living volcanic system into one that follows a predictable schedule. The next major structural failure remains tied to processes unfolding within the mountain itself, beyond any calendar created by people. That perspective gives the Sunda Strait its distinctive place among Earth's natural landscapes. This is neither an imagined danger nor a remote possibility discussed only in academic journals. It is a setting where volcanic growth, structural instability, and densely settled coastlines exist together every day. The rebuilding cone remains visible, the surrounding communities continue to expand, and the geological system that shaped both the land and the sea continues its patient work without interruption. Long before scientific instruments traced movement beneath the Sunda Strait, people living along these shores had already given the volcano a name that reflected long familiarity. Across generations, the Javanese knew the mountain that stood before the great eruption of 1883 as the Fire Mountain. The name carried no elaborate theory. It recognized a landscape that produced fertile fields, dark ash, glowing eruptions, and intervals of calm that could last longer than a human lifetime. Memory passed from one generation to the next, preserving the understanding that the mountain belonged to a rhythm extending far beyond any single life. When the caldera collapsed in 1883, the event reached distant continents with unprecedented speed. Telegraph cables carried reports across oceans until people in London, New York, and Batavia learned that something extraordinary had occurred before the full scale of the loss had even been measured. For the first time, a natural disaster became part of a shared global conversation almost as it unfolded. Newspapers printed fresh dispatches day after day, allowing people separated by thousands of kilometers, which is about 621 miles, to follow the same unfolding story while the landscape itself was still changing. More than a century later, another collapse entered worldwide awareness through an entirely different path. In 2018, a mobile telephone recording captured a concert beside the sea, only moments before the arrival of the tsunami. Within hours, those images had crossed continents through digital communication networks, reaching millions of viewers almost immediately. The mechanism of communication had changed beyond recognition, yet the geological process at the heart of the event belonged to the same volcanic system that had shaped the earlier catastrophe. During the years separating those moments, the volcano followed its own steady course. Fresh lava accumulated, slopes expanded outward, sections of unstable rock shifted under their increasing weight. Eruptions added new layers that concealed older surfaces, while the cone continued rebuilding after each episode of destruction. Satellites eventually recorded millimeter-scale deformation with remarkable precision, storing measurements that later revealed patterns already present before the flank collapse. Those observations waited within growing archives until improved analytical methods uncovered relationships that earlier generations could not fully recognize. Human society transformed repeatedly across the same span of time. Coastal populations expanded, ports handled increasing volumes of commerce, transportation networks connected larger cities, and scientific monitoring became more capable with every passing decade. Instruments multiplied across land, sea, and orbit, creating streams of information unimaginable during the 19th century. Messages that once required telegraph operators now traveled almost instantly through handheld devices carried in ordinary pockets. Every improvement expanded humanity's ability to observe, communicate, and prepare. The volcano itself remained untouched by those advances. Rising magma responded to pressure, temperature, and the movement of tectonic plates. Rock fractured according to its strength. Gravity acted whenever volcanic slopes became unstable. Ocean waves traveled outward at speeds determined by water depth and distance. None of those processes adjusted themselves to accommodate expanding cities, sophisticated technology, or faster communication. That enduring rhythm offers a perspective extending beyond any single eruption. Human knowledge continues to grow, each generation adding another layer of observation to the record. The volcano continues its own cycle with equal consistency, building, changing, and reshaping the landscape according to forces that began long before written history and will continue long after today's observations become part of tomorrow's archive. There are moments when a span of 100 years seems immense, enough to hold the rise and fall of nations, the growth of cities, and the lives of countless families. To the Krakatoa caldera, that same interval forms only a brief passage within a much longer rhythm. Geological evidence indicates that this volcanic system has existed in one form or another for at least 360,000 years, passing through repeated cycles of growth, collapse, renewal, and rebuilding with remarkable persistence. Every community that has ever lived beside the Sunda Strait has unknowingly occupied one chapter within that sequence. Kingdoms traded across these waters. Fishing villages became ports. Ports expanded into cities. Roads stretched across coastlines, once crossed only by footpaths. Throughout those changing eras, the volcano continued responding to forces operating deep within Earth's interior, following a pace measured in centuries and millennia instead of human generations. The settlements rebuilt after the catastrophe of 1883 rose during one of these intervals between major episodes. Houses returned to familiar shorelines. Fields produced crops once more. Harbors welcomed ships, and children eventually grew up with no personal memory of the eruption that had transformed the landscape. Stability became an ordinary expectation, even though the geological system itself had never reached an ending. It had entered another stage of the same continuing cycle. A similar interval shaped the years leading to 2018. Beach resorts appeared along attractive stretches of coastline. Visitors gathered beside the sea, drawn by sunsets, volcanic scenery, and warm tropical waters. 135 years separated the caldera, forming eruption from the flank collapse that generated the volcanic tsunami. For those living through that period, the passage of time felt long enough to suggest permanence. Within the perspective of the volcano, it represented another pause during an ongoing process of reconstruction. Today, another interval has begun. Fishing villages continue repairing boats and homes. Resorts welcome visitors again. New roads, buildings, and coastal infrastructure continue appearing across western Java and southern Sumatra. Families establish businesses and communities with every expectation that tomorrow will resemble today. The duration of this present interval cannot be measured in advance. Geological records reveal repeated pauses between significant events, yet they offer no calendar describing exactly when one chapter closes and another begins. One difference separates the present from every earlier pause. For the first time in the history of this volcanic system, people can observe its behavior almost continuously. Satellites repeatedly pass overhead, recording changes in ground elevation. Instruments detect volcanic tremor beneath the cone. Deformation measurements reveal subtle shifts across the growing edifice. Ocean sensors watch the surrounding waters, while researchers combine these observations into increasingly detailed models describing how the volcano evolves through time. Knowledge has therefore expanded beyond anything available to previous generations. Scientists understand far more about caldera formation, flank instability, tsunami generation, and volcanic rebuilding than they did only a few decades ago. Patterns that once appeared disconnected now fit together within a coherent geological framework developed through decades of observation, measurement, and comparison. The volcano itself continues without awareness of those discoveries. Magma rises when conditions permit. Rock accumulates until gravity reshapes it. Collapse gives way to renewed construction, and renewed construction gradually prepares the landscape for another transformation. Human understanding now follows that rhythm more closely than ever before, while the cycle itself continues with the same patient continuity that has carried it across hundreds of thousands of years. History often gives the impression that disasters belong to the past, arranged into chapters with clear beginnings and endings. Libraries preserve them in books, museums preserve their fragments, and generations inherit their stories as completed memories. Anak Krakatau occupies a different place in that pattern. It has not settled into history. It continues to write its own record, layer by layer, while observers measure each new change as it unfolds. The eruption of 1883 became a finished event, however immense its consequences remained. Its ash settled across oceans, its waves reached distant shores, and its effects entered scientific literature, public memory, and cultural imagination. Researchers could reconstruct its sequence from deposits, eyewitness accounts, and physical evidence. Every new study refined understanding of something that had already happened. The volcano responsible for that catastrophe had collapsed into the sea, leaving behind a caldera that marked the closing of one dramatic episode. Anak Krakatau belongs to another category entirely. Its cone continues rising from the caldera created by that earlier collapse. Fresh lava, volcanic ash, and fragmented rock steadily reshape its slopes. Small eruptions continue to alter its outline, while gravity and internal pressure constantly adjust the balance between construction and instability. Scientists watching today are not reconstructing a finished narrative. They are observing an active process whose later chapters have not yet been written. This distinction changes the nature of every observation collected around the volcano. Each seismic tremor becomes part of a continuing conversation between rising magma and surrounding rock. Every measurement of ground deformation records another moment in the island's gradual evolution. Thermal imagery, satellite observations, ocean monitoring, and field surveys all contribute pieces to a picture that remains incomplete because the geological process itself remains incomplete. The central challenge, therefore, belongs to the present rather than the past. Researchers understand far more about flank instability than they did before the collapse of 2018. They recognize patterns that were overlooked during earlier years, including gradual outward movement, changing heat distribution, and relationships between eruptive activity and structural weakness. These discoveries emerge through careful analysis after the event, allowing scientists to recognize combinations of signals that had already existed within the growing archive of observations. Those observations had never been absent. Nearly 12 years of satellite measurements recorded the changing surface before the collapse occurred. The information existed, preserved within successive images collected during repeated orbital passes. Only afterward did those records reveal a progression pointing toward failure. What had appeared to be ordinary volcanic behavior acquired new meaning once the sequence could be viewed in its entirety. Today, the same kinds of measurements continue arriving from the volcano with greater frequency and improved precision. Scientists examine them using methods developed directly from the lessons of 2018, searching for relationships that earlier generations could not fully recognize. The instruments have become more capable, the analytical models more refined, and the understanding of volcanic collapse more complete than before. Even so, the essential task remains unchanged. Each new stream of information asks whether familiar signals are gathering into a recognizable pattern or describing an entirely different path. Anak Krakatau continues growing while that question accompanies every observation, inviting science to interpret the living volcano with greater clarity than was possible before, one measurement at a time, within a story that still unfolds across the Sunda Strait. Every improvement in observation extends human understanding a little farther. Yet the volcano itself continues, according to forces that neither acknowledge nor respond to that attention. Instruments can surround the island, satellites can cross the sky on precise orbital paths, and researchers can compare thousands of measurements collected across many years. None of those efforts reaches into the conduit, carrying magma upward through fractured rock. The physical processes unfolding within the Earth remain governed by energy that has been flowing through this region for millions of years. The descending tectonic plate continues its steady descent beneath the neighboring plate, producing fresh magma that rises whenever pathways become available. Each eruption adds new layers of ash, lava, and fragmented stone to the growing cone. Every deposit changes the volcano's shape by a small amount. Gravity never stops acting upon those accumulating materials. The southwestern flank, therefore, continues evolving as fresh rock is added above older deposits that have already been weakened by heat, fractures, circulating fluids, and repeated eruptive activity. Scientists now understand that this gradual reshaping deserves constant attention. Measurements of ground movement can reveal acceleration before collapse. Thermal observations can identify changes in heat escaping from the volcanic structure. Seismic records can distinguish shifts in the character of internal tremor as magma follows different pathways. Combined together, these observations provide a richer picture than existed before the collapse of 2018. They illuminate processes that once appeared disconnected, allowing researchers to recognize developing instability with greater confidence than previous generations could achieve. Even the clearest picture has limits imposed by time itself. A structural failure may occur only after months of detectable change, or it may unfold following signals that become unmistakable only shortly before collapse. Nature does not promise that every important transition will announce itself with equal clarity. Some episodes leave long sequences of recognizable clues, while others compress critical changes into much shorter intervals that challenge every monitoring network. Should another major flank failure occur, warning systems may detect the event almost immediately. Messages can travel through communication networks within moments. Emergency agencies can begin established response procedures, and coastal communities can react according to evacuation plans refined through repeated training. Those advances represent genuine progress born from careful study and difficult experience. The movement of water across the Sunda Strait, however, follows the same physical laws that governed earlier disasters. Once a large mass of volcanic rock enters the sea, the resulting waves travel according to distance, depth, and gravity. Nearby coastlines still possess only a narrow interval between detection and arrival. Approximately 24 minutes remain available under circumstances similar to the collapse of 2018. Better preparation makes those minutes more effective, although it cannot create additional ones. The contrast across generations reveals how scientific knowledge changes outcomes without altering geology. During 1883, communities possessed neither warning networks nor an accepted understanding of volcanic tsunamis generated by collapsing islands. By 2018, monitoring systems existed, although they focused on different hazards. Today, those systems are broader, faster, and informed by lessons drawn directly from that collapse. The volcano continues its own rhythm without adjustment, while human understanding advances through observation, memory, and patient refinement, seeking each time to place fewer lives within the path of the moving sea. Morning light often reaches the Sunda Strait before the day's boats leave their harbors. Volcanic islands rise from clear water, their slopes outlined against the horizon with a calm presence that has attracted travelers, artists, fishermen, and scientists alike. From many points along the surrounding coast, Anak Krakatau appears as another striking feature of the landscape, joined by Rakata, Sertung, and Panjang, whose silhouettes preserve the outline of a much older volcanic story. Their beauty asks for no explanation. It exists as naturally as the sea that surrounds them. The richness of this region extends far beyond its scenery. Across western Java, generations have cultivated fields nourished by volcanic ash carried through countless eruptions over many centuries. Minerals released from weathered volcanic rock replenish the soil, supporting harvests that have sustained communities for longer than written history records. Rivers transport these nutrients across broad plains before reaching the coast, where marine ecosystems also benefit from the continual exchange between land and sea. Fish flourish in productive waters shaped by the same geological forces working beneath the strait. Life has also reclaimed the islands themselves with remarkable persistence. More than 140 years have passed since the devastation of 1883, allowing forests on Rakata to mature into thriving ecosystems filled with birds, insects, flowering plants, reptiles, and countless smaller organisms. Every generation of living things has contributed another layer to this recovery, transforming bare volcanic surfaces into one of the world's most valuable records of ecological succession. Scientists continue studying these forests because they preserve an almost uninterrupted account of how complex communities emerge after complete destruction. None of these gifts exists apart from the volcanic system that created them. Fertile farmland, productive fisheries, rugged coastlines, and islands that inspire exploration all originate from the same geological engine that has also produced destructive eruptions, collapsing volcanic flanks, and powerful tsunamis. The energy rising from deep within the earth expresses itself through many outcomes. Some unfold across centuries as landscapes gradually become richer for life. Others arrive within minutes, reshaping coastlines and altering human history with startling speed. This relationship appears wherever active volcanism meets human settlement. On the slopes of Mount Etna, vineyards flourish across fertile ground created by repeated lava flows. Around Mount Vesuvius, communities have long cultivated productive farmland despite the mountain's well-documented history. Far across the Pacific Ocean, Mount Rainier stands above growing cities, while glaciers and volcanic rock share the same towering summit. Different continents, climates, and cultures reveal the same enduring partnership between creation and destruction. People remain drawn to these landscapes because the advantages are tangible and immediate. Productive fields, abundant fisheries, reliable water supplies, and dramatic scenery encourage settlement despite known hazards. Families establish homes, ports expand, roads multiply, and visitors arrive to experience places shaped by remarkable geology. Each generation inherits both the rewards and the responsibilities carried by living within an active volcanic region. The Sunda Strait therefore reflects a pattern found across much of the Earth. Geological energy builds environments capable of extraordinary biological richness while retaining the capacity for profound change. Beauty and danger are woven from the same planetary process, expressed through different moments within an uninterrupted cycle that continues shaping land, sea, forests, and human lives together, just as it has for thousands of years. At the center of the great caldera carved into the floor of the Sunda Strait by the eruption of 1883, Anak Krakatau continues its work. Ash rises from the summit in recurring bursts. Lava reaches upward from the crater before falling back across fresh volcanic slopes. Each eruption leaves another thin layer of rock, another addition to a landscape that has never stopped reshaping itself. Growth arrives through repetition, one eruption after another, each contributing a small piece to a structure that exists only because earlier structures collapsed before it. From a distance, these eruptions belong to the ordinary rhythm of an active volcano. Ash columns climb several kilometers, which is about 2 miles, before winds carry fine particles across the surrounding sea. During darker hours, glowing lava fountains can sometimes be seen from the shores of Java, tracing brief arcs above the summit before returning to the crater. Fresh deposits accumulate across the southwestern flank, adding weight to the same side of the volcano that has drawn the closest scientific attention throughout recent years. Researchers continue measuring that flank with exceptional care because it carries a memory preserved in rock as clearly as any written archive. Between 2006 and 2018, the slope shifted approximately 15 meters, which is about 49 feet, toward the sea. The movement unfolded gradually enough that it blended into the background of ordinary volcanic activity until the collapse revealed what those measurements had been recording all along. Every new survey now asks whether similar patterns are beginning to emerge once more within the growing volcanic cone. The mountain standing today remains smaller than it was before the collapse of December 22, 2018. Even so, rebuilding has continued through successive eruptions, restoring material that once disappeared into the sea. Fresh lava hardens into new rock. Loose volcanic fragments settle across older deposits. Heat alters minerals within the cone, while underground pathways guide rising magma toward the surface. The internal framework that supported the earlier failure is gradually being replaced by another, shaped through the same geological processes that have operated since the island first emerged above the water. None of this places the volcano on the edge of immediate catastrophe. Current scientific evidence allows no responsible prediction that another major collapse will occur within a particular year, month, or season. The approach toward a comparable geometry may require many decades, and it could unfold across an even longer span. The essential point comes directly from observations published through peer-reviewed monitoring during 2026. The volcano continues rebuilding exactly as active volcanic systems are expected to rebuild, following physical laws that remain consistent whether people are watching or not. Above the Sunda Strait, Satellites continue crossing their established orbits with unwavering regularity. Their instruments compare one pass with the next, detecting changes measured in millimeters, while ground stations, ocean sensors, and volcanic observatories contribute their own observations to the same expanding record. Together, they form the most complete portrait this volcano has ever offered. The child born from Earth's most violent eruption remains active. The caldera beneath it remains unchanged, and each new measurement becomes another page in a story still being written, one careful observation at a time.